Okay, so we're here. And I think I got to the point that I understood what is it that it's happening. Yeah, why were we using the the sort of difference between what was predicted and what was true as a as a beef, right? But then I couldn't really. I guess I lost the session. Some model settings. Usage of advanced pacing. Okay. Um, I don't remember where I left. I left it at, yeah, exactly. So, and I think this is just essentially wrong, as in like we remember. I would have to go back in history, but I remember that, or the original implementation. I think it just did. Maybe I can actually get to it by means of just looking at the history. Self logits minus y. Was that the initial implementation at all? Not so sure. This was it, because I think I had already been doing some of my stuff in here with this reshaping and the logits and whatever for the softmax. So why? Wait a second. This kind of maybe seems like the derivative of something, isn't it? I think so. This is the dot product and then times 1 minus np power of like, this is definitely something. I'm not so sure if I still have this. But I was trying to see, was it like logits minus y? Was it really like this? It's happening 2 months ago. I'm not so sure if this is what the original. So I had like. So I think either was in main or something like that, because I had everything in one file, right? So here, I'm still doing like 6 months ago training example. I was still doing 2 months ago. At some point, I kind of had that whole thing in here. Copy paste it. So I don't know. Maybe not worth digging into. But I have the feeling that one of the things that I should be looking at is, I somehow just, I have the feeling that, or in the original implementation that Ghostwriter suggested, it was actually not looking at the array. It was looking literally. It was actually just looking at the predicted sort of the ground truth, like the probability of the predicted, the probability of the sort of the predicted word, kind of, and then comparing it to the the true value. Be what the the loss function is doing here. something like, taking a look at stuff like that. It kind of misled me into a lot of things because I was asking, basically, when I was asking Ghostwriter, it totally I mean, I don't know, did it actually mislead me? That's the problem. It's complicated, right? So, because I was like chatting to Ghostwriter, I remember, and he was like, and Ghostwriter was like, oh yeah, that's the equivalent of doing the derivative, right? Which I'm not so sure if it's a statement you can make. I mean, what you can say here is all you care is because the loss function that you're using is sort of the, if you just do the log, the logarithmic, negative logarithmic, right? The negative log. Essentially, you're just doing like it's a loss function that is literally just based on like how far off you are, right? So looking at actually how far off you are is already the kind of like good first step. I'm not so sure if I'm kind of ready to understand the next step, but anyway, I think the question that I had here in the last session was why. So why in the example that Ghostwriter was giving me, we were doing some sort of multiplying something by the derivative of the activation function. And now I kind of realize that that's maybe just because of the chain rule. That's just that's what it is, right? Because you want to calculate the derivatives of each of the tensors, right? And because some of them are composites, right? So this is basically the tangent of the hyperbolic tangent of z1, which is then in and of itself is something that is the function of x. And then the chain rule kind of says something like how you do that, right? So you actually have to do the derivative of these. That's why you're doing the derivative of these functions. But when so I think that is an explanation. I think that is just the math tell you to do so, right? And again, you're trying to find the derivative because the derivative tells you sort of a value and a direction in which you can modify something to minimize its value. And because we know we want to minimize a specific cost function, right? Because that's all we care. What we care is just minimizing a given cost function, which is kind of minimizing the error, right? And so you start with something. So similar the forward pass, and then the backward pass. I'm doing it like this, but whatever. I think that's what I'm also kind of getting wrong here, right? I think that. So let's look at these. So here we should simulate the difference between the predicted and the truth, but that's kind of like that's not all we want to do, right? We've got something which is basically we should just simulate an output. So if we want to simulate an output, we're not going to call these a tool. well, yeah, you can do that, right? The output is basically the output is just like your vocabulary of length, right? It's just different. It's just basically, yeah, you can minus that. No, I don't know. I mean, I don't know, man. It's still not. I don't understand that first step. I don't really understand that first step. How can I understand that first step? So backpropagation, 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 backpropagation. So we've got basically a situation where we have uh, an output array or tensor. We have an output tensor. Then this output tensor is calculated by multiplying something by something and adding something, right? So there's these different elements in here. This is how we calculate the output tensor, and or apply the softmax. That's kind of how we do it. So let's talk to ghostwriter. So it's either in our network the following forward pass. Where y is the output tensor, the output tensor. Given a given a the output tensor prediction. Yeah, output tensor exactly. Given tensor y true that represents the correct output. How do we implement backpropagation? My assumption is that assumption so far is that we start off calculating the difference between output tensors. But then, of course, then we need to basically, essentially what we want to modify is tensors W1, W2, B1, and B2, right? How do we get to the changes that need to be applied to W2? The error. Explain these step by step with some examples if needed. Okay, so assuming you're using cross entropy loss, your loss is calculated like this: y true times log y. So we need to calculate the derivatives of the loss with respect to all our parameters. Yeah, I mean that is the function we're trying to minimize, right? But the parameters are like y. The parameter is just the output vector, the output tensor, right? we calculate derivative loss with respect to W1, W2, B1, B2. Starting off with the upper layer, it's like a W2. So first we calculate the derivative of the loss with respect to Z2. For softmax activation and cross entropy loss, DZ2 simplifies to these. Okay, so that is just right out of the bat. Okay, that's the just a step they explain. Like, but I don't know. Like, I'd like to dive into simplification, but let's assume that we understand that's correct. Then to get the laws of with respect to W2, we have to calculate the derivative of Z2, the derivative of Z2 with respect to W2. Wait a second. The derivative of Z2 with respect to W2. Why? So the derivative of the loss we should need to calculate, right? Why Z2? The derivative of the loss with respect to W2. Yeah, I think that's a hiccup here. Is equal to the derivative of Z2 with respect to W2 times the derivative of the loss of W. Okay. So it's literally chain rule, right? So let's I know this should be easy, but let's make sure that I understand this. Let's take that as an assumption, okay? That's correct. This is a simplification. That is correct. Then we need to calculate the derivative. Okay, no, that's correct. I just didn't read that well. So we need to get the derivative of the loss function with respect derivative of the loss function with respect to W2. Funny thing. Okay, so that's another question. It's like why do we know that is then what we need? Loss function. Yeah. Okay. Whatever. Like, how do we know that that's going to give us something that we can then use to modify W2? Okay. First, let's just think through these. The derivative W2 the derivative of the loss with respect to W2, right? So we have Y. Y is softmax of Z2. Z2 is like all this kind of stuff, right? So you can chain all these. You can chain all these, and then basically apply the chain rule. So by the chain rule, the derivative is equal to the derivative of Z2 Is it so? The derivatives of Z2 with respect to W2. The chain rule. The chain rule. Okay, so the chain rule. So y equals fu and u is gx, right? So the derivative of y with respect to x is basically the derivative of y. So if that's what you have, it's like f of gx, and then you want to do the derivative of y, which is to x, is that d derivative of y with respect to the derivative of u, and the derivative of u with respect to the derivative of x. That's just what the chain rule says. So essentially, that's what we are applying here. The derivative of the loss function is basically with respect to w2 is the loss function with respect to z2, because I think that confused me is the order here. So of z2, because that's kind of the parameter, and then z2 is right w2. Yeah, that's okay. That makes sense. Yes. The derivative. Okay, wait. Okay. This is where we get like, how is it possible the derivative of z2 with respect to w2 is a1? The derivative of z2 with respect to w2 is a1. Is it just because this is a1 dot product w2? Like, is it just that because it's simple? Like, if we were not working with tensors, right, this would be like z2 equals a1 times w2 plus v2, and then obviously the variable is w2, and so the derivative is just a1. Does this work like that? Okay, maybe it does. I didn't know that. I guess, I mean, don't really care, right? It's a dot product, so I don't know, but okay. And the derivative of loss with respect to tz2 the derivative of z2 that's z2, so it's the derivative of like the derivative of log what's the derivative of log y? Uh, 20 by y. So y is the derivative of the loss function with respect to z2 is just basically a constant times the logarithm of the variable. think I'm should be one divided should be the inverse, right? Then to get okay, so these are the adjustments to be made to W2 during backpropagation. Similar conditions would be needed for W1, W1, B2, with the chain rule as the guiding principle. Note that in practice, we include a learning rate to scale the adjustments to W or B, ensuring we don't make too drastic changes, and that's all fine. Yes, okay, but there's some essential first principles here. It's like assuming, okay, so this is just the math of like calculating these derivatives. The derivative of these softmax and cross entropy loss. It's a form of a cross entropy loss. Is it really like that? One divided by n minus one divided by n times the sum of label. For a multi-class problem where only one class can be correct, we only sum of the log probabilities of the correct class. Okay. Okay, but regardless of these, what is it called? Cross entropy, though. What's it called? Cross entropy. Imputed disorder, yeah. We're talking about the distance from the predicted probabilities distribution to the true distribution. Essentially, what bits we'll need if we encode symbols from one distribution, the distribution isn't the wrong distribution. Machine learning will use a present relation because it provides a useful way to compare the predicted probabilities from the softmax function in the case of multiple the true probabilities by the one hot encoded target variables. The lower the cross entropy, the more similar the predicted distribution is to the distribution. So during training, we eliminate the cross entropy loss. Okay. Anyway, where am I trying to get to? I'm trying to get to the fact that so this is still unclear. Why does this simplify to that? But okay. With softmax and cross entropy, but essentially what you're doing is you need to calculate the derivative of the loss with respect to Z2, right? Z2 is, you're trying to minimize the function. Z2 is your parameters. So like you start from sort of the, well, Z2 is, yeah, it's kind of your parameter, right? Because that's the input space for your loss function. So trying to see, you're trying to calculate how, what's the derivative with respect to Z2. It's like how does this, Z2 need to change for the loss function to be minimized. then when you have this one, when you have dz2, so I'm trying to explain to myself what is it that I'm trying to understand. When you have dz2, then what? Then you want to take a look at, because essentially you want to take, so then you want to take a look at the next parameter, right? Because you want to modify each input parameter so you can tweak the final result. So then you take a look at how much do I need to change W2. It's almost like that's the first question. It's not how much you need to change the output. Like it's more like the first question: how much do I need to? I want to calculate what's the derivative of the loss function with respect to W2. Right now, the loss function kind of starts from y, starts from the predicted value, and then W2 is kind of buried into the chain, sort of into the composition of functions, right? Go on, give me a second. Here. So you're exactly with respect to W2. That will naturally. The thing is, if I go back to this one here, see if it opens, right? So again, it might be wrong or whatever, right? But let's say you have this function, you want to know how to optimize it, right? So you have your loss, this loss function. So you have the loss function, and you kind of calculate the derivative, and then that derivative will tell you it will tell you how to change the input so that you, because it in a way it tells you like the change of rate, right? I'm my brain is a bit, because we're not evaluating. Are we evaluating? We're not doing any derivative, or we're not like. The derivative is a1 is a single. In this case, it's just a constant. dz2. Because the derivative should be of loss, then it's like the general rule d loss is equal to a1. So the derivative of z2 with respect to w2 is a1, and the derivative so you're trying to calculate the derivative of the loss with respect to w2. That is equal by the chain rule to d staff to the derivative of z2 with respect to w2, derivative of the loss with respect to 2z2, where but then z2 is just not a, it's just an actual thing. Like it's a value, it's not a function. Z2 is not a function of anything. Z2 is a constant, isn't it? Or Z2 is kind of like what I have. Do I need to instantiate this Z2? That's what I don't understand. in here. So how do they get to that, right? Because when I have my loss function, the derivative is still going to be a function, right? The derivative is still going to be a function. So how do I actually get a value? If the derivative is still going to be a function, how do I still get a value that I can apply to these? Like I get the step in general. I get the step of like you're calculating the loss with respect to this variable, right? So if so, let's try to make an example that is kind of more abstract, even more abstract, right? Which is, let's imagine that I have, plot, I don't know, like a simple function, like, I don't know, like a, well, I guess I know what it means. I guess what it means is, yes, you have to instantiate it to the point where you are at, right? Because that is what is going to give you the direction that you have to follow. So plot, so plot y equals x squared. Or plot me equals x squared. Plot it together with its derivative. Plot it together with its derivative. Okay, so let's see. Just make a s.python, and then we just take that and copy here, and then we go to the shell and we run python p.34. So okay, so this plots x squared and then it's derivative, right? Then plots go to the shell and write the same thing. So sometimes the output won't just open. I don't know why. Have them here as separate plots. Let's say that I'm at like 7.5, right? So I need to know. No. So this is x and this is the y-axis. So let's say that my input is 60, right? And that's just the tensor, right? And now I want to know how do I have to modify, because this gives me minus 7.5, but I want to get to a second. this is y, this is x, what am I doing? So let's say that my x is 5, right? And that gives me 20 something, okay? 25. Anyway, I want to minimize that, right? So the thing is, how do I have to modify x, right? So essentially, when I calculate the derivative is going to be this function. And if I give it a 5, this is going to tell me, it's going to give me like 10. So yeah, okay, fine, but then I just minus it? I just don't understand. Is it that you always have to? That's it. If you evaluate the same, oh, it actually is telling me the values here at the bottom. And that's just a very basic math problem that I'm having right now. Is it I have, this tells me how the derivative function is how is the rate of change, right? So it just should tell me what I need to apply to x. What's the change I need to apply to x to minimize that, right? But if I'm here, it's going to tell me minus, and then minus 10, which if I minus it, then it's adding x, which is taking me to the right place. The key here is the 0 value, where it tells me that I do nothing, because then I'm already here. But if I go below here, it's going to give me a negative number. So I kind of, if I subtract, but is it always like this? That if you subtract the value of the derivative at a point, in general, in optimization problems. Given a function, and value, given a function, given a function and an input, and I have to modify the input in order to minimize the output. So if I work on the derivative space, right? Is it always so that subtracting the instantiated value, the same input on the derivative, it's the right thing to do? If you want to find a local, so uncommon approach is to start at a random point, compute the gradient of the function at that point, and then take a step in that direction of the negative gradient, opposite of the negative gradient. Subtracting the gradient is a step. So the subtraction is just like, okay, because essentially but this is just a first principle problem that I'm having. It's just the derivative itself encodes the rate of change, right? So if I have an input, if I give you an input, it's just telling me what's the rate of change. Like if I have an input that's 5, but if I input that input into the derivative, it's going to tell me the rate of change at that moment. So I have to subtract that because it's positive 5, so it means it's growing. So I have to subtract that. And here's -5, so it means that it's growing. It's so I have to subtract that to kind of get, yeah, okay, that makes sense. Yes. Yeah, sorry, this was just going to just down a bit too much, I guess. I don't really think I needed to go that down. Maybe I do, because it just helps me understand why we're doing what we're doing. Anyway, I'm not so sure I kind of progressed a lot in this session, but I think I'm not so sure I understand where the instantiation here is happening exactly. You know what I mean? Calculating the loss with respect to something that is a concrete value, and then this times this is at 2. Yeah, that I'm not sure I get that yet. Need to work on this a bit more in terms of where it is that I'm instantiating W2 specifically, or that I'm using W2 specifically, right? And I need to dig into that a bit more. Anyway, see you next session.